Hello, everyone. This is the second in a series of lectures talking about Chapter 32. Today, we're going to be talking about spherical mirrors. So, we've seen ray diagrams using a simple cross section of a flat mirror, and there's many shapes a mirror can have. If you've ever been to a fun house at the circus, there's those fun mirrors that give you a funny looking reflection. For now, we'll just talk about two different types of mirrors. They all come from the same shape. They are spherical mirrors, so it just means that their shape is like part of a sphere. So you can imagine taking a tennis ball and cutting it in half. So you have half a tennis ball. What you have there then is half a sphere, and if you're looking at the green fuzzy side, then that would be one side, and if that was a mirror, it would reflect differently than the other side of the ball you cut in half. So all the stuff we talked about with the flat mirror, where you have an object and an image, you can also do the same thing for spherical mirrors, where if you know where the image is and you know the overall geometry of the mirror, you can figure out what kind of image it'll make. So in the pictures here, you can already see the two types of spherical mirrors possible. The image on the lower left shows you both types, the concave and the convex mirror. So the concave mirror is like when you cut the tennis ball in half and you take a half of that tennis ball and you look at it so that the green fuzzy side isn't facing you. What you look at is the underside of the tennis ball, where the center is away from you. So the edges of the ball are closer to you than the center. But if you turn it around and you're now seeing the fuzzy green side, the center is closer to you than the edges. So that's the difference between concave and convex. So just to talk about concave mirrors first, they're sometimes called converging mirrors since they tend to converge light rays from objects near. The geometry of the mirror essentially comes down to what its radius of curvature is. So the idea is that since a concave mirror has the shape of part of a sphere, then there must be some radius associated with it. The curvier the mirror is, the smaller the radius, right? You can imagine, like in the drawing here, if the radius was smaller, then the mirror would be more pinched in. It would look closer and closer to the letter C. If the radius gets bigger, the mirror becomes flatter. So theoretically, if the radius was, say, infinite, the mirror would be flat. But in this case, it's not, and it's curved inwards, so it's a concave mirror. You can also think of the word cave, like it's caved in, it's tended away from you. And so we're going to find then the center of curvature to be a point that's a radius of curvature away from the mirror that also goes through the center of the mirror. And from that, we're going to draw a principal axis that connects the center of curvature to the center of the mirror. So the principal axis essentially cuts the mirror in half. And another thing we're going to talk about is the fact that, right, this is again, it's a cross section of the mirror. You're kind of looking at it sideways, but you can place any object anywhere on this plane, and you will get an image. So in this case, the object's placed right in front of the mirror, right in the principal axis, and with a low reflection, you see how an image is being formed. And if you note, both incident rays kind of bend, kind of reflect into the principal axis and through it. So you can kind of see its converging effect taking place. It's worth pointing out, though, that I know we said that the reflected rays converge to form an image, and that is true for rays that are close to the principal axis. So from an object, you can draw many light rays coming out at many angles, but only those that make a small angle with the axis, called paraxial rays, will actually converge through the image point. If you look at the drawing on the right, there's about 4 incident rays. The 2 that are closest to the axis do pass through where the image is formed, but the 2 that are the exteriors do not. They reflect off and don't converge at the image point. So this means that then the reflection isn't composed of all the light rays coming off the object. So the image isn't fully focused. And so there's going to be some blurriness in the reflection. And that's just due to, again, the fact that some light rays, are incident far from the principal axis. They're hitting the kind of edges of the mirror. So this effect is known as spherical aberration, and it's a realistic effect that all mirrors have it to some extent. So now you don't have to have an object placed on the principal axis. It can be some vertical, some altitude, up or down from that axis, and wherever it is, you can figure out where the reflection is going to be formed, where the image is going to be. And all it takes is actually just to draw two rays coming from it. Again, this arrays, the assumption is that they make a small angle with the central axis, so they actually go through the image point. And with some geometry, with a lot of reflection, you can actually figure out that the magnification of the object, so whether the image, the reflection of the object, the image is bigger or smaller than the actual object, can actually be found out through the position of the image over the position of the object. And this is neat because then you don't even have to worry about how tall the object is. You can just know where it's located and where its image is going to be, which we'll calculate with the formula in a couple of slides. The only thing worth pointing out is that this formula has a negative sign. So it's negative image distance over the object distance. The negative sign basically accounts for the fact that if the image is being formed in front of the mirror, it's always upside down. So the magnification formula doesn't just account for the size of the image over the object, but also whether it's upright or upside down. So don't forget the sign, because every time the image is in front of the mirror, the magnification will be negative. If it's behind the mirror, it'll be positive magnification. We'll talk about this soon, but just keep that in mind. So another important property of the mirror is its focal point. So we said that the concave mirror tends to converge its incident light rays, so rays get reflected, so they kind of come into the central axis. Now, suppose that the object is so far away that all the incident rays are essentially parallel to each other, kind of like what's being shown in figure B. If that happens, then all the rays will come in parallel to the surface of the mirror, and they will all reflect in through a point that's halfway between the mirror and the center of curvature. This is the focal point of the mirror, and it's something that all mirrors have. Its location just depends, again, on the geometry of the surface. So, matter of fact, it depends on the radius of curvature, since you can always find the focal point by knowing the radius of curvature, dividing that by 2, and it tells you the distance between the focal point and the mirror. This distance is called the focal length and is represented by a lowercase f. So the focal length actually just depends on the curvature, again, just on the radius. It doesn't matter the material of the mirror, since light is just reflecting, there's no refraction, so there's no consideration, for index of refraction or anything like that. For Lenses, though, we'll see that the focal length for lenses does depend on the material because light passes through the lens. So the way that parallel light rays get focused will depend on the index of refraction of the material. What's more important is that there is a mirror equation shown here in the lower right, which relates the location of the object and its image based on the focal length of the mirror. So without even having to physically go up to a mirror and place an object to see where the reflection is, you can use the mirror equation to figure out where the image is going to be located by just knowing where the object is and what the focal length of the mirror is. Picture A shows you a kind of realistic ray diagram of what parallel light rays do. So you see how they all pass through a point, and where they cross, you can kind of tell that it's kind of halfway through the radius of that mirror. So here's an example of a converging lens. So a satellite dish, while not the typical mirror you'd see in a house, it's still a mirror since it reflects microwaves and radio waves. In this case, this is a satellite antenna for satellite television. So basically, signals sent from network satellites towards the Earth. These dishes reflect the satellite signals into a receiver, and it lets you watch a couple of exciting TV channels. So this dish is a mirror since it's reflecting electromagnetic radiation. Even though it's not the mirrors we're used to that reflect visible light, it's still doing the same thing a mirror does. Now, the other type of spherical mirror is the convex one, where it looks like it's tented towards you, and the images that they form are usually they make the objects look a lot smaller and usually have a much bigger field of view. So the light rays tend to diverge away once they reflect off convex mirrors. That's why sometimes they're called diverging mirrors. And because of that, because incident light rays incident light rays actually diverge away from the surface, it looks like the reflected rays are coming from behind the mirror. And that means then that all reflections created by convex mirrors are virtual, because the reflected rays only appear to originate behind the mirror. So the image point for a convex mirror is actually always behind the surface of the mirror. And no matter where you place the object, even if it's far or close from the mirror, the image it creates is always going to be upright, and it's generally going to be smaller than the object. If the object is right at the surface of the mirror, it'll be the same size. But if you pull the object away from the mirror, so you increase p, the image is going to be smaller. Also, it's worth pointing out that when an image appears behind the mirror, when it's virtual, it's always upright. When it's in front of the mirror, it's upside down. Now, the mirror equation that we've seen for the concave lens is the same for the convex one. You just have to be careful about the signs on P and Q and F. So overall, the object being on the real physical world means that the object distance P is positive. If the reflection is appearing to come from behind the mirror, then that means that the image distance is negative. If it's a real image, so it comes the reflected rays physically converge in front of the mirror, then Q will be positive and the image will be upside down. The convex mirrors, so we're talking about the ones we're just discussing that tend to diverge light, their focal points are always behind the mirror. So if you shoot a bunch of parallel rays towards any convex mirror, the light beams will fan out away from the mirror, and so the focal point is virtual. It appears to be behind the mirror for all convex mirrors. So in the mirror formula, the focal length f will have a negative value. For concave mirrors, the focal point is in front of it, so it's positive. So how do we figure out where the image is? Well, we have already seen the lens equation where if you know the object distance and the focal length of the mirror, they'll tell you where the image will be formed. There's another way to do this using ray diagrams, which are actually a quick and dirty way to figure out the image by drawing just a few incident and reflected rays at key paths through the axis. And it's just a nice way to show what's going on in terms of rays and give you an idea of what the image will be like. So you have the mirror formula and you have the ability to draw the mirror image and object, so you have a way to kind of double check your math. So once you know where your object is and what the mirror's geometry is, then you want to start off by drawing the location of the object, the focal length, and the center of curvature all to proper scale. And this is very important because otherwise you will not get a proper image if things are not at the proper distances. So what you want to do is, if you have a concave mirror, once you establish your object and your focal length and center of curvature, you're going to draw 3 rays. The first one, shown in blue in either drawing, is going to be parallel to the principal axis, and it's going to always reflect through the focal point. In the case that the focal point is in the case of a concave mirror, the focal point is real, so it always reflects through. The ray number 2, which is the green one, the incident part of it goes straight through the focal point and then reflects parallel to the principal axis. The third one you draw, shown in red, this one has a angle of reflection equal to 0. So it hits the mirror right at the normal, and so it reflects back in the same direction. This ray will always pass through. So when you draw the ray number 3, it's just a ray that crosses the center of curvature. Doing so, drawing a ray from the object through the center of curvature guarantees that the reflected ray will be sent backwards in the same direction. So basically, ray number 1 starts off parallel, bounces off through the focal point. Ray number 2 goes through the focal point, bounces off parallel. And ray number 3 goes through the center of curvature and bounces off in the same direction it came from. So no matter where the object is, by drawing these 3 rays, you save a lot of time in taking out a protractor and figuring out the geometry of all the reflections. Now, once you have these rays, you can find out where the image is formed by finding where the 3 rays intersect. Now, you only actually need to draw 2 rays and find their intersection, and that will be where the image forms. But by drawing 3 rays, you can have extra confirmation that you drew everything right. So how do you find the image? Well, the image location is where the 3 reflected rays intersect. For a object facing a concave mirror that's far from the principal axis, the image will be real and upside down and smaller than the object. So you can see the ray diagram on the left is showing you that, how the three rays intersect below the principal axis in front of the mirror. But concave mirrors also have a special case. If the object is really close to the mirror, if it's between the focal length and the mirror itself, then the image will actually be virtual. If you look at the reflected rays in the second picture here, the reflected rays are not physically converging anywhere. They don't meet, but it looks like they converge behind the mirror. So when this happens, when the object is within the focal length, then the image will be virtual, it'll be upright, and generally it'll be bigger than the object, it'll be magnified. Ray diagrams for a convex mirror are again the same thing. The first ray is parallel, the second ray goes through the focal point, and the third ray bounces back and forth in the same direction. The difference here is that since the focus and the center of curvature are virtual, the rays don't actually go through the focal point or the center, they just appear to. And also, because the object is on the other side of the focal length of the focal point, all images formed by a convex mirror are on the other side of the mirror. So all images are virtual, they're always going to be upright, and generally they're going to be smaller than the actual object. Note, though, that as if you bring the object closer to the mirror, the image is also going to come closer and it's going to be bigger up to being the same size as the object. If you pull the object away from the mirror, you are going to see the image move farther away from the mirror the other way and get smaller. So, quick quiz. You want to start a fire. So you're going to reflect some sunlight using a mirror, and you got a bit of kindling in your wood pile to start it. So you want to focus light onto that kindling paper. And the question is, okay, well, what's the best choice of mirror? Well, you want to use a mirror that focuses light, and that's going to be the convex mirror. Sorry, the concave one. The concave one, again, is it's like dented inwards, so it tends to bring light in. You can get that focusing into the kindling and start a fire. Maybe have some marshmallows. Okay, so this is a photograph of scientists working on the primary mirror of the Hubble Space Telescope. The question is, based on the reflection that you see, what kind of mirror could this be? So let's talk about the reflection. The reflection is upright, so that means it's virtual. That means that the light rays, the reflected light rays, appear to converge behind the mirror. Secondly, we can't actually see the objects in this photograph, by the way. The object in this case are the scientists that you see in the mirror's reflection. These four scientists are somewhere off camera, but by comparison, though, if you look at the scientists who are just like on the ground adjusting the mirror, you can't see the reflection, but just note the size difference, right? The scientists on the floor, that's give us an idea of what a real person to scale what their size of a normal person is. But the scientists in that reflection, though, look a lot bigger. In other words, this means that the image is magnified. And if that's true, so if the image is virtual and it's magnified, the only mirror that does this is the concave mirror. Convex mirrors tend to make the image smaller. Concave ones, when they create a virtual image, make it bigger. Anyways, next time we're going to talk about images formed by refraction, so I hope you join me then.